Welcome everyone to the 2023 edition of February Flare Up, Climate Change and Climate Adaptation. For those of you I've not had the pleasure of meeting yet, I'm Karen Bluen. I'm the Research Coordinator at Canada Wildfire. Before I hand over the reins to our session moderator, I would like to provide a brief explanation of what February Flare Up is and how it came about. In 2021, Canada Wildfire facilitated Fuels Friday, 4 interactive online sessions exploring wildland fuels, characteristics, and measuring techniques. Upon review of Fuels Friday workshop, we decided to create a yearly online series concentrated on one topic, a blitz of information and discussion. In that vein, we decided to focus on remote sensing and remote sensing applications in 2022. And this year, we're really excited to kick off the Climate Change and Climate Adaptation series. It's also worth noting that the interest in and feedback we received following Fuels Friday and the remote sensing series provided a catalyst to add in regular monthly webinars. We are now 1 year into this endeavor. We're beyond thankful for the participation both from our presenters and our viewers. Our goal is to provide a space where research and wildfire operations and planning can collide. If you have a topic you'd like to see us cover, please reach out via the chat box or by emailing us at wildfire@ualberta.ca. And with that, welcome to February Flare Up Climate Change Edition. We are so happy to have you here and hope you enjoy. I'm going to hand over the reins to Brian, who will be our moderator.
And I certainly will echo Karen's comments. We're glad that you're able to join us. And I'm just keeping an eye off to one side here of the waiting room. People are continuing to flow in, but we'll get going here. And as she said, this is week 1 of 4, and I think it will be a very interesting set of programs. Just wanted to let you know today that I'm actually working from a location in Southern Ontario that happens to be on the Between the Lakes Purchase, or Upper Canada Treaty 3, which is different, of course, from Treaty 3 on the prairies, which is mostly Southern Manitoba and Southern Saskatchewan. The participants that I see on the board here basically come from across Canada, so they're basically in a lot of different treaty areas, as well as some people who are coming to us from unceded lands. One of the things that I think is an interesting exercise that is worth doing more than once is to take a look at the treaty document or the treaty language that actually applies to where you are actually living. And you have to look at that in the context that that treaty was written between basically it was Britain, the king, and the local First Nations, the indigenous peoples there. And the context of that, what's written down, doesn't really make much sense, or doesn't make enough sense by itself. And so you always have to take a look at how that actually fit into the cultural and legal frameworks of the two parties in the treaties. And so it's a very interesting exercise, and I think a very important one for all of us if we want to really be aware and to promote that we're meeting our side of the treaty, making our obligations realized. So today we're going to start on the introduction sort of level of climate, and to start the day off, I actually called up Dave Phillips and spent a little time with him to just basically, as I was going to say, use the warm-up act for sort of our main presentation today. And many of you will have seen Dave Phillips on the radio, or perhaps you know about his weather calendar that he coordinated for many years. His probably most well-known sort of TV presentation is the Canada Weather Top 10 that shows up both on TV and a lot of other news outlets. But he is really sort of the climate spokesman extraordinaire. And it's also worth noting that Dave was, for me and for just looking at the names here, a number of others here who studied as operational meteorologists, was our instructor on climate issues when we were training to be operational meteorologists. And so he has a long history with Environment Canada and has been a very effective spokesman getting the message across. And so I have a couple questions, a couple clips from our interview that I wanted to play this morning. And then we will proceed on with basically a little bit deeper dive into the whole issue. So here's about 4.5 minutes of my chat with Dave. Can you tell us, what is the difference between weather and climate?
Well, Brian, thank you for those kind words of introduction. And you're right. I think it's a good start. I mean, hey, I often think Canadians blur the distinction between what is weather and what is climate. And I don't mind that. I'm sometimes introduced as the senior climatologist or the senior meteorologist. And hey, we're just kind of weather people. And so I think that really suffices. But I think it's kind of interesting to distinguish between what is weather and what is climate. I had a friend once who was a meteorologist, and she said, knowing I was a climatologist, David, climate is dead weather. And I thought, well, how cruel but how clever that is. I mean, it's probably, and I think we are certainly involved with dead weather, historical weather. It's over, it's past. And certainly meteorologists forecasting today's weather sees yesterday's weather as dead weather. I mean, they're moving on. They're more interested in forecasting today and the next couple of days. But also climate is about futuristic. What is the future going to be? Not necessarily next tomorrow or the next day, but next month, next season, next year, next decade, the next century. So I think that works. I think that my sort of working definition of climate is sort of it's sort of climate is what you get, and no, climate is what you expect, and weather is what you get. I think that kind of works. But the old age definition when I was studying climatology university was average weather, and that used to frost me. I think, my gosh, I mean, climate is more than just average weather. I mean, to know that the average annual temperature in Edmonton is 2.3. What does that do to you? I mean, that has no meaning at all unless you're comparing with Rome or Moscow or some other place. Of course, we often say that that people buy clothes because of the climate, but we wear them because of the weather. Okay, that works except for teenagers because they dress like in Southern California no matter what the weather. But what I kind of like is kind of a new age one. It's climate is like your personality, but weather's like your mood. We sort of have a personality, maybe we're born with it and we stay with it for pretty well most of our life. And that's the climate, but weather, we know the mood can change from 2 or 3 times during the day. The one though, I think your audience might reflect on is this one. It's that famous line about everybody talks about the weather, but nobody does anything about it. It was, incorrectly credited to Mark Twain. He said he didn't say it. I think it was his editor acting. So everybody talks about the weather, but nobody does anything about it. Well, climate is everybody does something about it, i.e. we change it, but we don't want to talk about it. We don't want to own up to the fact that perhaps we're changing it. So I think those are some of the kind of definitions and nuances that help to explain what is weather and what is climate.
Why has climate become such an important environmental issue in recent years?
Well, Brian, I think it is. I mean, we hear a lot of people saying that climate change is the most important environmental issue that humankind has ever faced. I think someone once said to me, well, climate is too important to be left to the climatologists. Hey, another cruel line, but they're absolutely right. And the progress we've seen in the science of climate and the understanding of climate change, both globally and at home, is when glaciologists and forest botanists and oceanographers and geologists and modelers and even the social science got involved in trying to understand what this subject is about and how it really does affect our weather. I think really, I mean, we've come to realize that if you change the climate, you change the weather. They're inseparable. I mean, and I think that's an important consideration to recognize. I think we've also realized that weather extremes and climate-related disasters are on the increase, and that likely human beings are having a part to play in that. I mean, it is something that I think it's been argued that we can do something about it. I mean, if we've created the problem, then perhaps maybe we have the solution to help us overcome what is this important issue. I mean, some people think you can control the weather. I don't think you can. The Russians and Chinese, they think they can see clouds and cause to stop raining when you want it to, or to rain when you want it to, or to stop hailstones from falling. I think it's a lot of science fiction. I think the jury is still out on that. But I think there is this great interplay between what is happening globally and then what is happening, of course, locally in terms of the effect of weather and climate from soil, from lakes, from terrain, from vegetation. And so I think it is, therefore, I think a very important environmental issue. It cuts across all boundaries. And so I think that is what I think that why climate has become a very important environmental issue.
So with that as sort of a little bit of very broad overview kind of context, we have the good fortune of having Jeremy Fyke join us today to take the sort of introduction or the fundamentals of climate in a little bit of deeper way. So I will turn over the floor or the screen, I guess, to Jeremy. And thank you very much for being with us. We're really glad you were able to join us.
Awesome. Thanks for having me. Let me share my screen. Awesome and great. Maybe I'll leave it up to you, Brian, or anyone. If I go mute or you just you lose your view of me, just let me know, and I'll stop. Right. So thanks for having me to the February flare-up, which is, by the way, is just a classic name. I've been in the climate world for a while. And there's lots of speaker series, and they always have, like, to be honest, quite geeky names of climate, variability talk or whatever. And so February flare-up is a classic fire geek title for a seminar series. And I'm allowed to say that because I'm a geek too. So thanks for having me for this February flare-up talk, which kicks off, as I understand, kind of a month of thinking about how climate change and wildfire interact and how to adapt to wildfire planning and stuff to the changing climate. I'm from Environment and Climate Change Canada, and specifically the Canadian Centre for Climate Services, which is a little subgroup of that big ECCC monster that does work to try and translate climate information, especially but not limited to understanding of what future climate might look like, into actual decision making and on the ground real world thinking. And so it's really fun to come to a group like this, which is definitely involved in some pretty consequential real world thinking around wildfire, and think about some of the fundamentals of what we're talking about when we say climate and climate system and climate change. I am coming at you from British Columbia, the Okanagan Valley, which is the unceded territory of traditional unceded territory of the Silks people, who have a thing or two to teach us here in the Okanagan about how to manage wildfire. We are learning. Settlers are learning belatedly. And so there's a lot of neat interactions there, I can say from experience, between our Western knowledge that I'll kind of focus on today, and really amazing depth of knowledge from traditional knowledge sources like the Silks people where I'm at. Right. I'll get going. What I'm going to aim for here is about an hour-ish of me yapping up. But what I'd like to do is open the table to questions and discussions and stuff in the remaining time. So just to give you a sense of the timeline here, I'll try and keep it to an hour or so, and then we can have a chat. Right. Oh, okay, good. So what I structured this talk as today is a bit of a step back from specifically focusing on climate and wildfire. The idea being that it's important to understand the basic system that you're working within your particular specialization in order to be effective at understanding how, in your case, wildfire and climate relate. So this is going to be sort of a step back to general climate system and climate science. I've peppered it with as many examples and case studies from the wildfire context as possible. But what we are doing here is stepping back a bit to basic climate system understanding and climate science. And what I'm trying to do here is frame some of this learning over the next hour or so in the context of answering some of these pretty basic sounding questions. What is the climate? In quotes, what does that actually mean when we say the climate? Because that certainly helps us understand the phrase climate change. It understands to help the system that you're looking at if you want to understand how it's changing over time. To understand the climate, we are well advised to understand what influences the climate. And so we'll talk a bit about things that can give the climate system a kick over time, including not least us. And then I'll spend a bit of time talking about this question: why is climate, quote, uncertain? We can dig in a bit to what this word uncertain means, and then unpack why we sometimes think of the climate system as uncertain, and why, in fact, it's really interesting and useful to understand what we know and what we don't know about the climate, because that has a real bearing on our ability to plan and adapt to it in the future. So we're going to try and step through these general questions, but we're going to unpack each of them, and as part of that unpacking, do some basic learning about important aspects of the climate system. Some of this may be old news to some of you, and some of it may be new news. We're going to go back to some fundamentals. I can say, though, I think going back to these fundamentals, even if you know them already, is good to do. Since my undergrad, I've been kind of marinating in climate science and the climate system. It's useful for me, even after 15 whatever years of playing in this game, to go back and once in a while just review the basics of what the climate actually is. It really helps when we're doing our actual applied work. So we're going to structure this hour around these questions. The reason why it's good to go back to the basics is because we often dive into the climate change conversation and climate change work with putting ourselves with the cart a bit ahead of the horse. We use words a lot like projections and variability and models and bias and downscaling and adaptation and extremes and mitigation. These are words that are ultra important in our work to understand and respond to climate and climate change. But underlying all that stuff needs to be an understanding of what the climate system is and what the system is we're actually talking about. And so the idea here is to set up a bit of this understanding in this talk, so when we get into these more complicated downstream topics of adaptation and future and future projections and stuff, we kind of know what we're talking about. So the idea is, after this talk, you can come back to these words with a bit more of a basis of understanding of what lies under the hood. Okay, let's start with a basic motivation. I like doing this. Why would we bother to understand the climate system? What's the value in going out and studying the system that we see when we look out the window? Well, I've tried to boil it down to a basic motivating statement here. We rely on the climate system in a really very fundamental sense. If it wasn't here, we wouldn't be here. And so it's just seems like it's important to understand why and how it's changed, both in the past, why it looks like it does in the present, and the holy grail question, right? Like, what might it look like moving forward into the future? This is, to me, has a lot of analogies to history, right? We study history not because it's just cool to understand what people did in the past, but it really does inform how we perceive our own situation in the present, and actually how, we as humans might evolve into the future. The study of history is important, not just for the sake of it, but to understand our place and understand what's impacting us. And so I think the same thing applies to actually study of the climate system. It has real human relevance, and it's not just academically interesting. Preaching to the choir here, but I think it's important to sometimes step back and think about this. Understanding why and how it's changing is really important for us as a society. So climate change has been happening since the Earth has been around, billions and billions of years. And there's some great examples of past climate change that actually motivated me back in the day to get into climate science. In particular, I wasn't motivated by trying to save the world or anything. I was just actually blown away, in particular, by things like the Ice Age. This is a map of about 21,000 years ago, planet Earth. Those big blue blobs are the big ice sheets that existed not too long ago in geologic time. Of course, the question is, this is crazy climate change. Why did this happen? How did it happen? To answer that kind of question, we've got to go down to a deeper understanding of the climate system, understand how it works and the processes that are involved in it. These are massive, by the way. This is a fantastic cartoon. Thanks to XKCD Comics. If you ever want to while away an afternoon looking at amazing science geek comments, go to this website. These are present day skylines of some big cities, including some in Canada, Toronto and Montreal, overlain with how thick the ice was due to climate change in these locations about 21,000 years ago at the peak of the last ice age, the last glacial maximum. That's crazy, right? Climate change is a big thing. At the time when the ice was, over a kilometer above the top of the CN Tower in Toronto, sea level was also about 100 meters, over 100 meters lower than it is today. So there's big potential for climate to change in big ways. And we can see that just by looking into the past, let alone thinking about what's going to happen in the future. Understanding this stuff just seems intuitively important to me. And this is just eye candy that at least motivated me. It's not wildfire, but I thought I'd put it up here to give you a sense of the big things that climate change can do. Now, climate change just naturally in the past has also gone in to a remarkable magnitude in the other direction. There's been some really amazing stuff coming out recently analyzing like paleo DNA. So people digging through, I don't know what dirt and stuff is not my specialty, but actually analyzing the DNA of entire ecosystems from like 1 million years ago. So what they've done in this amazing example is gone up to the northern tip of Greenland, which today is like really cold. It's like almost at the North Pole, and dug around, found some DNA, analyzed it, and recreated what Greenland looked like about 1 million years ago. So really, actually, I'm a geologist by training, so not that long ago. This is what it looked like. This is an artist's reconstruction of northern Greenland, which today is a barren, nearly the moon, basically. We had grass, bunnies, I guess those are mastodons or something, big warm mammals. We had trees, grasses, bugs. Climate change managed to warm the Arctic up to something that looks today like literally pretty close to where I am in southern Canada. Right, so climate change has happened in both directions over the time, and we can look back and find just incredible examples of the power of the Earth to change what it looks like over time. Those are big hand wavy examples. We can also dig down and look at really interesting signals of climate change in things that are kind of more relevant maybe to this cruise. So this is a set of records from a little lake actually in southern BC, just south of Revelstoke, British Columbia, Begbie Lake. What's shown here is a record. They've dug down into the native lake and pulled out a bunch of mud and silt and stuff and looked at the different types of trees, and not just trees, but other species of plants and stuff that grew and changed and evolved and came and went at this location over the last 14,000 years, right? So over essentially the Holocene, the last most recent, quote, stable period of climate in Earth's history. Lots of interesting stuff here, that lots of Latin names that I don't know. I think I know what Pinus is, but other than that, I don't know the other ones. But the point is there's big changes here over time in this location, just one location in Canada. And what's interesting here is they also looked at changes in fire in the paleoclimate context, in the past climate context in this location, and really interesting stuff looking at changes in what they estimate to be fire return intervals, fire event frequency, charcoal fluxes, which is, I think, the proxy they use to estimate this stuff. You can see big signals of change in this record due to changes in probably in large part to the climate of this one location in southern Canada over time. Lots of interesting stuff here. Why does this happen? We need to think about the climate system that this record comes from to understand not just the what, but the why and the how. It's important to study this stuff, is what I'm saying. That's all past, and it's fun to motivate thinking about climate change from looking at the past and being like, holy cow, why did that happen? But it's also maybe a little more societally relevant, let's say, to think about why and how current change is happening. This is a fantastic map. I love this one. You read it like a book. Each little blob there is a map of the world, and it goes from 1850s, read it like a book, whatever, left to right and down. The first one is year 1850. The last one is 2022, so last year. Each thing is a map of the world, and the colors, blue represents colder than average, than the long-term average, and red represents warmer, right? And so step back and blur your eyes, which is what you're supposed to do with this particular picture, and you just see that obvious signal of something happening, especially around and after kind of 1970s, 1980s, this kind of thing. It gets redder and redder and redder, and like less and less blue. There's still some dips and blue showing up here and there, but the picture is clear, right? The system is just visually getting warmer. This is just from observations of the Earth over time. So why is this happening? How is it happening? Again, it comes down to understanding the climate system that gives us these kind of records. And then the holy grail question is, well, okay, this is what's happening now. We want to try and plan for the future. We want to adapt our wildfire planning to be resilient for tomorrow, not just today. So what is this system going to turn into in the future, and why is it going to do that? These are questions that really benefit from a good understanding of just basically the system that we live in, the climate system. Now, climate science is the discipline that tries to answer these questions, the how and the why especially. And it's important to recognize that climate science is totally not a new discipline. In fact, give it a year and it'll be, in some official sense, like 200 years old, actually. And that comes because one of the seminal studies of this really ridiculously smart guy back in 1824, Fourier, spent a bit of time among solving all sorts of other problems to think about, quote, general remarks on the temperature of the terrestrial globe and planetary spaces. Dig down into this and you see strong echoes of what we today call climate science. And a lot of really important climate science work was done not last year, 10 years ago, 20 years. It was done like well over 100 years ago. Eunice Foote, for example, was one of the first scientists, female scientists on my dad, which is not, I don't think, wasn't an easy thing, certainly back then. She published, one of the first women to publish a physics paper in America, actually, possibly the first. This paper called Circumstances Affecting the Heat of the Sun's Rays, thinking about actually how CO2 operates. And then all the way forward to still quite a long time ago, Arrhenius in 1896 produced some of the first estimates of how much the Earth would warm if we put more CO2 into it. Those estimates are actually bang on still. We've added some more detail and fluff to them, but some of the basics of climate science to answer these how and why questions and think about the future, were done quite a long time ago. So climate science has been happening for quite some time already. It's important to note that when we sometimes hear in the media, for example, that climate science is this new controversial science. It's not. It's based on some really old, really established science. That was then. And what I'd like to do briefly is just think now about what, quote, modern climate science looks like. It's a really fascinating field that I would call it, maybe the best description is it's the mutt of a bunch of fundamental types of science. Here's my best Venn diagram of what climate science is. The best climate scientists, in my opinion, are people who are like a mile wide and an inch deep in a whole bunch of diverse fields, because all of these fields are really important contributors to our understanding of what's happening out there when we just look out the window, right? So physics is incredibly important. Geology is important. Math and stats is hugely important. I've overcome my fear of stats and learned to love stats because it's incredibly valuable in understanding the long-term picture of climate versus weather. Computer science, we run lots of models and we'll talk about these things in a little bit, but computer scientists are pretty key to the discipline of climate science, chemistry, biology, and even social science. Social science is critical here because humans are one of, if not the biggest geophysical influences on the planet today, and we're driven by our social behaviors. And so actually climate science relies really heavily on learnings from social science to understand how we are impacting the climate system. So modern climate science is a really multidisciplinary field. And a lot of people enter into this climate science discipline through really interesting pathways, through social science backgrounds and meteorology and physics backgrounds, chemistry, biology, et cetera. So it's really neat to work with people who sometimes self-identify as climate scientists because they come from not one discipline, but many. Now, modern climate science too, you can think of splitting it into two different threads or two different sectors is a bad word. observations and modeling. This really mirrors how a lot of other research and thinking about the world in general occur these days. On one hand, you have us looking out the window and trying to understand the system that we're interested in this case, climate, by just looking at it, measuring it, observing it. Now we can, in the climate sense, we can walk out the door with a mercury thermometer and stick it in the air and get a temperature measurement. That's super valuable. Those are some of our best records because people have been doing that for a while. But these days we can use our superhuman technological capabilities to observe the climate system in a remarkable number of ways. And this is just exploding now with things like satellites, real-time information coming down from space, terabytes coming down every day that we can dig through and understand. Of course, we can go out and look at climate from on the ground, but with not just our eyes, but incredible sensors and things. As a picture in the middle from people watching a forest fire in the States with some instrument that I have no idea what it is, but it looks really cool for research. We can send robotic autonomous vehicles swimming through the ocean for months at a time, and they surface every week to send their information that they found up to satellites. So we can look with our eyes, but we can also look with our technology and we can observe the system. On the other hand, especially with the advent of computers in the last half century or so, and the continuing explosion of computational technology, we can do what's called modeling, right? We can build representations of the system that we're interested in, the climate, or whatever other thing you're interested in. We can build that into computer models, and we can run those as, in a sense, like virtual labs that allow us to play with the system and understand it inside the computer instead of looking out into the real world. This is valuable because we can play with the system and experiment on the system in ways that we can't if we're just looking at the one realization that we have out there in the real world. So observations and modeling are two ways that we undertake climate science these days. This is really important, actually, practically, when you are working on some applied climate wildfire project or whatever, because especially in the context of understanding future changes to whatever you're interested in, you will almost certainly be ingesting information that's a combination of observations and modeling. And each of those types of information come with strengths and weaknesses, opportunities and caveats. And so it's pretty important actually to understand when you're doing this applied work in the climate wildfire interface, to understand on a case-by-case basis where the information is that you're getting and how it was developed. Was it developed on a computer by some person in a windowless room? That was me for a while, so I can say that. Or was it developed by someone out groveling through the real world with a mercury thermometer or a satellite or whatever? Those are different sources of information trying to describe the same thing, but in different ways. So modern climate science, super interdisciplinary and informed, especially now by kind of this equally weighted, let's say, mixture of observations and modeling. And the best science and the best understanding of how climate change is happening comes when you have these Venn diagrams of disciplines and techniques coming together. Okay, that was some philosophical rambling, but I thought I'd get it out. What I want to do now is turn to this basic question. What are we talking about when we say, quote, the climate? Can we define that a little better? This is a fantastic image that is a combination of a bunch of observations. So I'm going to use the word observation there. This is us looking at the planet, but it actually combines a bunch of different observations, I think in this case, mostly from satellites, and overmaps them with each other. And when we do this, we can see that the climate, the thing we live in, is super complicated, right? There's ice growing and contracting on land and in the ocean and on the rivers and lakes. There's the ocean with crazy circulation and eddies and things that carry important biology with it, phytoplankton, which is actually the color we're seeing here in this image. And kind of same thing on land, right? There's biology moving back and forth. There's differences in the physical characteristics of a point as you move through this yearly cycle. This is a really complicated system, and it's kind of a bit mind-blowing to think about it all at once. And so a nice thing to do is to break this climate system down into its constituent components, just to clarify what we're talking about here. So we can do that. It's actually pretty easy to do. And when you see this next plot, you'll be like, oh yeah, this is too simple, but it's important to do this every once in a while just to sometimes get back out of the vortex you're in. So climate components, we have the atmosphere. This is the thing that we probably know the most about intuitively because we live in this every day. There's the ocean. This is actually the driver of the climate system. We live on an aqua planet. And so in many cases, the rest of these things come along for the ride, depending on what the ocean wants to do. There's the land. We know this one pretty well too, because we tend to walk on it a lot. It goes down below our feet and it interfaces, of course, with the ocean and the atmosphere. Ice is worth considering separately. It behaves in really unique ways, and it's really important when it comes and goes. We have ice on land. You know, I'm looking out and seeing some snow out my window here. We have ice that grows on lakes. We have ice that grows underground, like permafrost. We have ice that grows on the ocean, like sea ice. And if you leave enough snow on the ground for long enough and keep piling it up, we have glaciers on land, and actually glaciers that flow into the ocean too. So ice exists in a lot of places, and it's worth considering ice separately because it behaves quite differently than everything else we have. And then the last kind of canonical component of the climate is life, the biosphere. And the biosphere life, up to and including big creatures like us, are not just participants in the climate system. They're not just observers in the climate system. They're really participants as well. And the biosphere is as equal a member here as the rest of these physical components. So this is kind of a picture of the climate. So when we say the climate at a very general level, we're talking about these five super major, general components. You can dig into each of them separately, and people do, right? Oceanography is a study of one of these components, in particular, the ocean. Atmospheric dynamics, meteorology tends to focus on the atmosphere, biology in the biosphere, geology on land, glaciology on ice. And so for centuries, essentially, people have been studying these things and learning a lot about how complex they are. Where it becomes interesting, though, and where it becomes a real climate system is when we think about how these components interact with each other, right? They interact all the time to the order of millions of tons per second or whatever, just massive interactions and conversations between themselves all the time, every day, day and night, 24/7. We can show those interactions. We can make those interactions schematic through these two-way arrows. So for example, the atmosphere is always talking to the ocean, and the ocean is always talking back to the atmosphere, often moderated by the biosphere and the ocean. Same thing across all the other components. These are called couplings between these climate components. And these couplings are as important, if not more important, than the behavior of the components themselves in isolation, let's say. Okay. They control huge and important things. El Nino is just one of many, many examples. What are these conversations like? You can split them into two different types of conversations. There's conversations, interactions that are made up of fluxes of mass. So things like water evaporating off the ocean into the atmosphere, for example, or raining back down from the atmosphere to the ocean or over land. That's a flux of mass of H2O, that chemical species H2O. But we also have conversations, fluxes of all sorts of other mass, different chemical species, right? And even different biology. So we have carbon fluxes, we've got dust and aerosol fluxes, etc. So fluxes of mass are one way that these components interact with each other. The other one is fluxes of energy, equally important as fluxes of mass. So we have heat moving from one to the other all the time. We've got kinetic energy momentum. Think of wind blowing on the ocean or blowing on land and lifting dust or moving waves. That's a transfer of energy. It's a conversation between one component and the other that moves energy from one to the other. And so in general, you can think about these components, the fluxes between them, and specifically fluxes of mass and energy as the most basic description of the climate that you can make. It's really important, though. This is a real fundamental schematic of the climate system. You can build back up from this to really complicated pictures whenever you want. We've heard, since we were probably kids, maybe teenagers or whatever, things like the water cycle. The water cycle is just a colloquial way of saying fluxes of energy and mass between different components of the climate system with respect to that H2O, the water. We have the carbon cycle, which is just conversations, fluxes between different components of the climate system but for carbon in the different chemical ways that carbon exists on the planet today. And when we dig into these cycles, what we see is just those conversations happening between the components of the system and what influences those transfers of mass and energy around the planet. Carbon, of course, both of these have direct relevance to wildfire. You even see a little wildfire. If you look closely on the carbon cycle, it's being blasted by a cute little lightning bolt. Of course, fire has a real regulating and moderating role in not just these cycles, but lots of other cycles that happen in the coupled climate system. Maybe the last kind of thing to think about carefully when we're trying to define the climate system is that it's a global system. We can't really think of the climate system as a bunch of local systems that don't interact with their neighbors. The climate is global, and trying to understand climate globally and even locally really means we have to step back and think about this whole system at once. And you can see examples of that just by looking at a weather map. This is from relatively recently, a snapshot of just weather on a particular day. The circle, I think, is somewhere around Edmonton, maybe close. And we can see just from here that the weather in Edmonton on this particular snapshot is being influenced not just by what's happening, 100 kilometers around that point, but indeed by what's happening way out in the North Pacific, which in turn is being influenced by what's happening on the other side of the planet, north and south, east and west. So to understand even local climate, you have to typically step back and think about what's happening globally. So it's a global system, and it's coupled between these different important components. Okay, so we know what the climate system is now. Let's think about the difference between it and weather. We've heard a bit about this already from Dave Phillips. Great analogies, and I wrote them down myself because they're awesome. Here's one maybe a bit more formal definition of weather: state of the system, particularly in a particular location over a short period of time. In this example, it's really a snapshot, and we see some clouds and some places that are sunny and cloudy, but it's the snapshot of the system in a short period of time. What I'm going to do next is show a climatological view of this and focus on the clouds. Right here, we see clouds existing in one place and not existing in others. That's a snapshot of weather. Here's a snapshot. Well, I shouldn't say snapshot. A picture of the same thing, but in a climatological sense. This is a map, a 30-year average map of cloud fraction. So over time, how much time is typically spent sunny versus cloudy in a particular point all over the world. So the light color, the white color here means cloudy lots, very cloudy areas in general. The general personality of those areas is cloudy, even though sometimes they have a sunny mood, to borrow the analogy of Dave. And the blue areas are where it's the personality is generally sunny. And what's interesting here is you actually start to see now much more stronger echoes of important biogeoclimatic zones across the world. We see the Sahara stand out in this map of cloud fraction, for example, and we see the Amazon stand out as well as being a really cloudy area. The point here, partly, is that climate can be, in many cases, is the determinant of, well, the personality of these regions versus the individual mood day by day. It can be sunny in the Amazon every once in a while, and it can also be rainy in the Sahara. But the climate, the long-term average, or I should say statistical conditions over these regions, is really a strong determinant of how they look and becomes climatological. We talk about weather and climate too very differently in terms of how we present and understand information. So these are two plots of weather versus climate for Toronto. The one on the left is very recent projection, a look back. No, this is a forecast actually that I got of weather. This is temperature in Toronto over a week or so period at the end of January. And what we see here is an actual attempt to understand day by day what the temperature will be in Toronto. On the right, we have a representation of Toronto's climate, and it's different than the representation of weather. We have the average monthly temperatures averaged over, in this case, 30 years, and plotted against each other. And we get different information out of these types of plots, right? On the left, we say, oh, we better bring some sunscreen or a toque, whatever. On the right, we get information about the average seasonal cycle of temperatures in Toronto. And so we can ask different types of questions if we're asking weather questions versus climate questions. Okay, that was a quick run through of, in a nutshell, what the climate system is. And now we're going to turn a little bit to what influences the climate. And the analogy here I take is we just described the soccer ball, how it looks, and what the constituents of that soccer ball is. Now we're going to turn to descriptions of what can kick that soccer ball and make it move and change, what can make climate change. So we're going to run through a laundry list of natural things that can cause climate to change, as well as human things that can cause it to change. So we're going to start with the most basic one, the sun. This is our flaming neighbor that gives us a huge amount of energy day in and day out. And it really drives the system. It gives us a huge and necessary kick. It gives us a lot of energy. If you look at the units of the y-axis here, this is the amount of energy that's coming in at the top of the atmosphere. It's about 1,300 watts per square meter. And that's about like 1,500 watt light bulbs shining down day in and day out on that space for every square meter of the planet. So a huge amount of energy coming in, and it drives the system to do all the things that it does. That energy changes over time, though. We have 11-year solar cycles, goes up and down by a couple watts. And over time, the amplitude of those changes, and we see a plot of that here from actually back to 1850 of these solar cycles and how they varied over time. That changes, and so you expect that if that changes enough, we can get a change in climate. And indeed, in the past, this has been potentially the case. This is one potential kick that we get. Actually, another important kick that caused a couple kilometers of ice to grow above Montreal and Toronto and lots of other places in Canada is changes to the Earth's orbit over time. The Earth doesn't go around the sun nice and well behaved and in an ever-changing manner. It actually operates kind of like a wobbly top, albeit with the wobbles and changes in the shape of its orbit happening over timescales of like tens to hundreds of thousands of years. And so this work was originally figured out by a fellow named Milutin Milankovic as he was a prisoner of war during the First World War, imprisoned in the Budapest Library. He asked for that because he wanted to do a bunch of studies. But he came up with this really amazing description of how the Earth's orbit changes over time, and changes to this orbit tilt the wobble and the shape, the level of circularity of the orbit, have over long time periods huge impacts for climate, the ice ages, for example. So these are some extraterrestrial or like astronomical kicks that can cause climate to change. Here is some examples that exist on the planet, but these are kicks that are sort of external still to the climate system and can come in and make the climate system do things, make it move in a different way. First one is volcanoes. Volcanoes are great and powerful influences on the climate. This is a picture of the 2022 eruption. Let's see if I can get this name right. I'm not going to try the name. It was near to Tonga, a remarkably powerful eruption. And you can see how big it was by this satellite image of the thing. When eruptions are big enough, they can blast a lot of things up high into the atmosphere. And the most important thing in many cases that they blast up is really fine dust, really fine dust, actually called aerosols. What that does potentially is shade the planet because it reflects some of the light coming in before it can get to the surface of the Earth. So in many cases, volcanoes can kick the climate and actually make it cooler, at least for a short period of time, even a couple of years. The plot on the right is called aerosol optical depth, and the big spikes in these, which correspond to reasonable coolings of the planet over a couple of years, correspond to the big volcanic eruptions. Pinatubo you can pick out, Krakatoa, El Chichon, and others show up here. These are great ways to kick the climate. Over really long time scales, plate tectonics is great at changing climate in big ways. As these continents move around and shift their place on the planet, the ocean circulation has to change. And where deserts and jungles and things like that, ice sheets change over time as well. So this becomes a really powerful way for climate over, of course, like million-year timescales to change. Plate tectonics is a great kick to the climate soccer ball. Those are often things that, except volcanoes, I should have added comets here. Comets are a fantastic way to change the climate. The dinosaurs will tell us that. These are things that typically they'll operate on long time scales, and we understand them quite well. We have data to play with them, but we also are able to influence the climate ourselves, and we do that in a few really important, particularly important ways. On one hand, we emit greenhouse gases to the atmosphere. So we add to the fluxes of these greenhouse gases that are already naturally occurring with an additional kick that we essentially dig up in terms of fossilized carbon and for the most part, and put into the atmosphere much quicker than it would otherwise go. We do that through all the activities that make our modern society modern. We drive cars, we heat our houses here in Canada. That's pretty critical. And lots of other things that ultimately cause concentrations of these radiatively active greenhouse gases to go up in the atmosphere. These are some of the most important records we have in climate science and climate systems understanding. These are records of CO2 concentration change in the atmosphere over time since the 1960s when these records started, and these are ongoing. And as well, methane, another important greenhouse gas, and both of these are going up, and we can understand how that influences the climate, how that causes a kick to the climate. We do other things though, besides emit greenhouse gases that impact the climate, that can cause the climate to change. Another important one is actually essentially very fine dust aerosols that we kick up through our activities into the atmosphere. These are sort of the same things that volcanoes do, but we do that as well. So we add to that aerosol load in the atmosphere, and that, as you can see in this picture, which comes from agricultural burning in the Amazon, that can cause changes to how much sun actually makes it through. It becomes hazy, and that influences the climate. So greenhouse gases, aerosols, land use changes, we can influence in other ways. The big ones are greenhouse gas emissions and actually aerosols. They're important enough, these influences, that I thought I'd take a quick segue here and just talk briefly about exactly how they work in terms of influencing the climate. And they do that through their effect on Earth's radiative budget. And we'll step through that really briefly in a couple minutes here. So what we do is, as we know, we get energy from the sun, and it comes through space and hits the Earth. Actually, only about 50% of that energy makes it down to the surface of the Earth. The remaining 50% gets reflected away before it even gets to us by things like clouds, things like aerosols, and even reflections just off the surface of the Earth. So snow, for example, is a great reflector. The reflectivity of different parts of the Earth is super important. It's called albedo. And so a lot of the energy from the sun doesn't even make it that 1300 watts per square meter. We get about something like 600-700 of that on a long-term average down to the surface. The rest of it goes blasting back into space and doesn't even have a chance to impact the climate system. This is where aerosols come in, right? They influence how much is actually reflected back to space. And so our human influence there is by blocking the sunlight before it even gets into the system. Greenhouse gases, though, are a bit different. And starting to understand how greenhouse gases influence the climate comes down to understanding how the Earth sends energy back out to space. It comes in a shortwave, but then the Earth transforms that. It sends it back up as infrared heat, kind of heat that we can feel. And what that does is, what happens then in the atmosphere is the greenhouse gases trap that type of energy and then re-radiate some of it back down. And so greenhouse gases act by blanketing the Earth with gases that are opaque to this outgoing heat. And they trap some of it and essentially send 50% of it back down instead of letting it all escape to space. This is a good thing, because without this, we would be much colder than we would need to survive. But we add more greenhouse gases, and that's what causes the system to warm up. We can understand how strong all of these kicks are, and these are great and complicated plots that describe these different levels of kicks. When we study them all, we can see, for example, that the total anthropogenic kick is much bigger than the other kicks that are relevant on our timescales, strength of the sun type of thing. And so this is one important piece of evidence that tells us that we are causing the climate change that we see today. And it's not being caused by natural kicks to the system. The other aspect that's important here to understand in understanding the climate system is the act of feedbacks on the system. We kick it through, let's say, adding more CO2, and that causes some climate warming. Let's say that causes increased fires, which cause increased CO2 emissions that wouldn't be there otherwise. That causes an enhanced greenhouse effect, and that causes greater warming, right? This is a positive feedback. In this sense, it's not emotionally positive, it's positive in the physical sense. It's amplifying the original change that we introduced by adding some CO2. We also have negative feedbacks. Fires arguably cause increased reflection. They increase the albedo of the planet. That can cool things, and that will cause less warming than we would have otherwise experienced, right? So we have positive and negative feedbacks, and understanding that these are in operation and can make the response of the system a little more complicated than it would have otherwise been, is an important factor of understanding the climate system. All right, in this last section here, what I'm going to do is run through this question and try and think about climate uncertainty, because we hear about it a lot, and unpacking what that means is important to dealing with it in a robust way, and also learning from the system through understanding and studying the uncertainty. Uncertainty comes in a few different flavors. There's some stuff that we are uncertain about. We have limited knowledge of just because that's a fact of life and we'll never have that knowledge. But there's other uncertainty that we can try and reduce through better understanding of the thing we're studying, in this case, the climate system. And we can reduce that uncertainty by learning more about it. So here's a picture of a climate parameter, right? Let's call it temperature. And let's say we want to understand what the temperature will be like at a particular place, XY location on the planet, and a particular time, let's say out in the future sometime. We don't know exactly what this number is going to be. And we don't know that for kind of three really important reasons that contribute to our uncertainty here. So it's somewhere in this box, and we don't know where exactly in the box this number is, because of three sources of uncertainty: natural, internal variability uncertainty, model uncertainty, and scenario uncertainty. And what I'm going to do now in a few minutes is just try and unpack each of these. Understanding what these are at some level is a really important aspect of doing applied climate work in any field, let alone wildfire climate work. So we're going to do a quick unpack of these sources of uncertainty in climate. We'll start with model uncertainty. We talked a little bit about what modeling is, and a really important tool in the global climate change context is using global climate or Earth system models to simulate the climate and try and send it forward into the future, in many cases, to understand what climate will look like, not today, but tomorrow. So we're going to go back to this schematic and think about how we turn that into a computer program, basically. First of all, we take this super complicated system and make it into a bunch of little bricks. We discretize the system, to put it in mathematical terms. And then we run all those little bricks representing all the pieces of the climate system. We turn those into computer code, and we run those often on some really, really big computers. And this is in a nutshell what a climate model is. And we use that to send our understanding of the climate system forward in time into the future as best we can. Now, these models have become more and more complicated over time. And that's a good thing, complex, because they're including more and more processes that we understand are important to the overall climate picture that we are looking at when we look out the window. So they started out quite simply. Actually, they started out as tools to understand the effect of nuclear winter. Some of the first climate models came out of nuclear weapons labs. And they've developed since then, thankfully, into more robust tools that include everything from interactive vegetation through to marine ecosystems, sea ice, etc. So they've got more complicated. And they've also gotten a lot more numerous. So today we have, upwards of 20, 30 big climate modeling groups producing these really complex programs and running them worldwide. This is a map from the CMIP-5 project, but the CMIP-6 is similarly inter-comparisons of climate model output. So we have lots of complex models developed by different people. And some of the operational meteorologists will know if you play with different weather forecast models, you might get slightly different results, right, for the same experiment that you undertake. And this is true with climate models too. One way that we like to look at differences in climate models, a really canonical way is through what's called their climate sensitivity. And this is a real simple experiment. You take a climate model and you double the CO2 and you wait for a while and you see how much the globe warmed. That's all it is. It's a real standardized experiment that all the models do. And when we do that, we can see that the different climate models respond differently. We have some models that are quite a bit more sensitive. Actually, the most sensitive these days seems to be the Canadian model. It, in this case, warms by like 5.6 degrees global average when you double CO2 in this idealized experiment. Down to INM, this is the Russian model actually. In this particular suite, it's the least sensitive, it warms by 1.8 degrees, right? They warm to different degrees, and this is an uncertainty. This is a model uncertainty because we use different models, same experiment, and we get different results. And this is the core of model uncertainty. We can understand this. We can swath it out, quantify it, and try and understand why it's happening. Okay, so that's model uncertainty. The next one is, we call it scenario uncertainty. And we talk a lot about climate scenarios. We use RCPs, SSPs. These are future estimates of what, in particular, humans will do in terms of greenhouse gas emissions, but also the other ways that we can influence climate. We don't know what humans are going to do in the future particularly well, right? And so we make scenarios that describe possible futures. These are uncertain because we don't know which one we're ultimately going to follow. When we pass these scenarios through climate models to get the climate change that we can make consistent with each of these emissions futures, we get a range of climate results. Here's some examples of that: ranges in global surface temperature changes, ranges in the rate and magnitude of sea ice loss in the Arctic. We're uncertain about which one these will actually be because we don't know what we, as really dominant geophysical influencers, we don't know which path we're going to take. And so this is uncertainty. This is scenario uncertainty. And we can look at this in a lot of different really unique ways, right? So we have model uncertainty because models are different, scenario uncertainty because we don't know exactly which pathway we're going to take. And the last source of uncertainty is natural internal variability. This is almost coming back to the weather conversation. The previous two sources of uncertainty are things that we can, in some sense, can control. We can make different models, we can make different scenarios, but this one is different. This is just a fact of life that we have to deal with in our estimate of what climate will look like, even what climate looks like today, let alone in the future. This is a plot. This might pique some operational meteorologists in the room. This is a set of simulations. This is model output, so not observations, but models of 7, in this case, different regional climate model runs. This is actually very much like weather forecast runs, except these started in year 1950, January 1st. They were tweaked slightly differently in each case by essentially the butterfly effect, a tiny little tweak to each of these models before they got kicked off. And lo and behold, after about the 2-week weather window, they all start to diverge in terms of their absolute pathways. So that after about 2 weeks, we can't say with too much certainty, well, weather is going to be warmer or colder to some degree. What we can say, what we are reduced to saying, is things about the statistics of that cloud of realities moving forward. This is the core of actually chaos theory, and that's an important aspect of climate science, is understanding that the climate system is actually technically a chaotic system. And what that means is that, like a pot of boiling water, we can't predict, when exactly a particular bubble is going to emerge or pop or move around, or a particular piece of convection is going to happen in that pot. But what we can say really well and in a well-constrained way is statistics of that pot, how hot it's going to be, how many bubbles per minute are going to come up. Same thing with the climate. And so this comes about from some really fundamental work in understanding the predictability of weather versus climate. And it boils down to the fact that the climate is this chaotic system. That sounds kind of confusing. I suggest you watch Jurassic Park. Jeff Goldblum in Jurassic Park provides one of the best descriptions of chaos and how it manifest in the real world in that movie. This is a snapshot from when he's doing it. I challenge you to find that and listen to it. It applies very well to the natural variability and uncertainty in the climate. So we take natural variability, this inability to exactly predict the weather, more than about 2 weeks out, and we extend that into the climate context. And even today, we realize that we can't define climate in terms of absolutes. We have to talk about it in a range of means and maxes and mins statistically. What that also means moving into the future is that this is a source of uncertainty for climate change projections, right? We have this cloud of climate change moving up instead of a particular pathway that we can say, year 2100, January 2, it's going to be -23. We can't make weather statements like that in the climatological context. What we can do, though, is talk about climate change in almost like a signal to noise kind of way. We can say, climate is obviously moving out of the past historical context, and we can describe that in really clear and useful statistical ways. We can talk about changes to the mean temperature or precipitation in this case. As we heard off the bat, though, that's not often all that useful. What maybe is more useful in the climate change context is talking about changes to the statistical properties of climate with respect to the extremes. Warmer extremes or wetter extremes in this case are going to get more severe, more frequent. Those dry extremes are going to also get more frequent, right? So we can talk about climate change not in terms of weather, but in terms of statistics. And this is because of this natural variability, uncertainty. So these are the three sources of uncertainty, in quotes, that we encounter when we're talking about climate in any context, especially as we move into the future when scenario and model uncertainty become important. Which uncertainty matters most? Where do we have to focus most of our time understanding and communicating when we're thinking about climate change? It depends on when, and it depends also on where. This is some great work that a colleague of ours at CCCS, Elaine Barrow, did in 2019, looking at which uncertainty bin matters most for prairies temperature. And she also did this for prairies precipitation and other things. Fantastic plot, takes a little while to think about though. What it's showing is that the relative contribution of each of these sources of kind of not knowing exactly what the conditions are over time. On the very left-hand side, we see that internal variability, basically weather, dominates. If your question is 1 or 2 years out into the future, best to think about which mode of El Nino you're in versus which climate scenario or which climate model you're using is one practical way to put that. But as you move forward in time on this plot, the green and the blue chunks get bigger and bigger. The slices of the pie get bigger and bigger, and that has implications too. We say if you're going up to year 2100, if your planning extends that far, then you do have to think about model uncertainty, which climate models you're using, and you do have to think about scenario uncertainty, which emission scenario you choose to follow. So lots of practical implications about thinking about related to thinking about which source of uncertainty is important for you for your particular application. All right, a final thought here, and then I'll wrap up, is a bit of a soapbox here, the difference between accuracy and precision when it comes to future climate projections in particular. Here's two shotgun scatters of a target, one of which is the target is trying to understand future climate in this case in a conceptual way. On the left, whoever's shooting that gun is having a very precise cluster. Everything's close together, but it's all based on present day information. And so with respect to future climate, it's super precise and also kind of like basically totally wrong. It's precisely wrong because they're using precise present day information, but we know that it's going to be less and less relevant to future change. So it looks good, it's very precise, but it's actually wrong, versus using, one could say, accurate but less precise results coming from this endeavor of climate modeling and combinations of modeling and observations. When you use that, you get less precise information, but it's more appropriately arranged around the target that you're interested in, which in this case, again, is future climate. And so in this case, you can argue that accuracy is actually more important than precision when it comes to trying to understand future climate, right? This is the argument in a nutshell for using things other than just historical observations to understand not today's climate, but tomorrow's climate, to understand future climate. Okay, so that was a whirlwind tour through some climate system fundamentals, and hopefully you enjoyed that. Hopefully Hopefully you're still around. In conclusion, right, we had some questions that we put up, and we used those questions to dive into some fundamental fundamental characteristics of the climate system. And we can summarize them here as best as possible in some Twitter-like statements. The climate is a set of coupled Earth system components that are linked and interact with each other, and they're influenced by natural forcings, natural things, kicks from outside the system, and as well as anthropogenic human kicks like CO2 and stuff like that. They're also influenced really strong. The climate system is influenced by feedbacks inside the system, both positive and negative feedbacks. Climate uncertainty is really important, fascinating thing to study and to understand just in the basic context of thinking about responding to climate change. Climate uncertainty comes from these three real canonical sources: model uncertainty, climate model uncertainty; scenario uncertainty, which is we don't really know what humans are going to do into the future; and then just this natural noise in the climate system, weather and interannual noise called natural variability. And understanding these and how they interact with each other, and which one you're most interested in exploring, depending on your time scale and location and stuff, is really important for when you're doing applied climate work, like the climate wildfire work that probably a lot of you are thinking about or even up to. So with that, I'll stop. Thank you for your time and having me. And I know I'm preempting maybe another advert on the same thing, but I've signed up for these myself because I'm pretty stoked on attending them. There's the next February flare up sessions talking about a bit more specifically about the climate wildfire context than I got into in my talk. Thank you, and maybe I'll stop sharing there. Does that make sense to the organizers?
Well, thank you very much, Jeremy. That was very thorough coverage of the ground. It's hard to figure out what you're all going to fit into only 60 minutes or so, but you, I think, have given us a lot of interesting information to think about, as well as presenting it in a way that's been really good. We don't have a ton of questions, but there is one, and I think it refers to slide number 8. I think that was sort of the breakdown of the little blocks of time, more or less a heat map of climate over time. And the question was, what data sources were used for that, or how many different data sources were used for that?
Right, so that's back to the thing you read like a book, if I get
Yes.
this question right.
I think that's the one. Yes. Yeah.
Now, yeah, that what's interesting about that plot, if you don't blur and actually you get in real close and look at it, is the pictures earlier in time, 1850, 1851. Those have a lot of missing data, like just basically white. And that reflects the fact that at that time, of course, we didn't have satellites, we didn't have as many ships driving over the ocean and airplanes flying around and weather balloons. So the information from back then was much more literally people with the thermometer, maybe on a ship, but often on land, and it's the gathering of that historical information. But over time, the map fills in until today, which is basically all covered because we got satellites. And so the source of information has changed, but a big part of making that kind of the data underlying that plot is homogenizing and standardizing that, so we know that we're comparing like to like when we're comparing an 1850s mercury thermometer with a satellite data set. So lots of different sources of information, and the biggest part of that work is just making sure they're all essentially apples to apples to make a pretty plot like that.
Excellent, thank you. Another question that has come up is basically, do modern climate models incorporate feedbacks that could push the climate into new modes? Things like significant methane release from permafrost melt, or the melting of, it says clathrates here, but I think that might be a typo, calthrates, frozen methane pockets.
They do, to the extent that the processes are integrated. So there's a ton of feedbacks in climate models, and that's kind of one of the main reasons why they don't look totally wonky when we run them and compare them to the real world. Feedbacks that are just obviously included by default and have been forever, basically, are like things like the albedo feedback. And this is that classic one where if you start to melt some snow off your driveway, an exposed dark driveway on that spring day, then your driveway will suddenly start melting faster because you have lower albedo, it's taking in more heat, melting more, positive feedback, run away, and soon your driveway is clear of snow. So things like that are no-brainers. There's other real fundamental feedbacks like water vapor feedbacks and things that have been in there forever. The feedbacks that are more challenging are feedbacks for processes that we don't have yet like super good handle on. So there's examples of that, like methane feedbacks. A lot of models do now have integrated permafrost components. And so when the Earth heats up in these virtual laboratories, indeed, the permafrost that simulated there melts and blasts more methane and CO2 into the atmosphere. But it's that process understanding is still, imprecise. And so the feedback there, the differences between those feedbacks as represented in the models is actually one of the big reasons why we have model uncertainty, because of differences in the strengths of the positive feedbacks. Some feedbacks are sort of still, like, to be honest, totally lacking. I know, because this is where I came from in my discipline, that Antarctica and sea level rise from Antarctica is like pretty much a dark horse in terms of how feedbacks are going to amplify or dampen its contribution to sea level rise, because Antarctica is super complicated, and that's not really well done in climate models yet. So there's a spectrum of feedbacks from fully nailed to, in some cases, almost absent. But the big ones that influence things like global temperature and changes in precip, those are generally down because they're so important that they got figured out like quite a while ago.
Thank you. And perhaps a question along the same kind of vein. Is there a question, or the question is, might there be things that we as a scientific community are really not even thinking about and that we're missing that could catch us off guard? The unknown unknowns, I think, threshold event, a number of different aspects there that are worth considering.
Yeah, Donald Rumsfeld would fit in well in climate science, but we have some optimism that there's not like horribly unknown unknowns. And I say that because when we integrate our best knowledge of the climate system into things like climate models, and we set, things like gravity and the albedo of snow to like the right values, and we press go on that climate model, which is our, description of our knowledge, basically all in one piece, it runs and looks pretty similar to what we see in the real world. And that's a source of confidence, right? If we ran it and it turned into Pluto or Venus, which I've done sometimes in my work with climate models, I break them and they look terrible. If it looks like the real world, in other words, we can validate the model as looking realistic, then it gives us confidence that we're not missing huge unknowns. There's always the potential of that stuff, but I think at this point in time, we're past that really terrifying feeling of thinking we're missing something entirely fundamental. We've had, like I said, a couple hundred years to sort through this, and our understanding matches with reality, and that's a good thing. So we never discount it. Climate scientists are always terrified of missing something, which partly motivates us to try and get everything we can. I think we're relatively there. The details, the devils are in the details, I think is safe, something kind of safe to say at this point.
Perfect, thanks very much. And then if we drill it down just a little bit more specifically, so the question is Environment and Climate Change Canada, or perhaps others, doing any specific research on changes, for example, in the polar vortex, and the fact that while the atmosphere has been warming, the stratosphere has been cooling. And so the question comes from a meteorologist who works in the Northwest Territories, and they're looking at climate change leading to some wacky vortices, and some strong weather systems over the past few years that have been very significant at the north.
Right. Yeah, this is maybe an example of a place where, okay, big picture, global average, we get it, but when it comes down to these really complex, really dynamical shifts in the statistics of meteorology, like how often the polar vortex wobbles or meanders or stays in a particular location. This is work that a lot of smart minds are working on now, not just in Canada as well, but not just in Canada, across the globe. So thinking about, how, first of all, how these things look today, but then how climate change all these kicks that we're giving to the system, how that's going to influence those dynamical systems. In some cases, people are starting to understand pretty well, but in other cases, and maybe polar vortexes is one of those, it's still kind of like, at least to second order and third order, like research topics. I think there is some good understanding of things like that at big scales, like how these things are impacted by global climate gradients and such. But then when it comes down to the details of, okay, well, how exactly many more of these are we going to experience? Or questions like that become tricky, and the subject of research versus us putting a ECCC stamp on it and saying, yep, this is where we're going with that kind of thing.
Thank you for your comments there. Appreciate that. That's very good. I think, unless I have missed something, that is the questions that have been posed. Oh, we got a new one here. And yeah, I guess it's related to that. Climate models, do they actually give a general sense of whether we could expect jet streams to oscillate more or less over time? If they do, and how would they inform that?
Good question. I to be honest, I don't have a great answer for, so I'm going to choose to get back to you later on that one. I can do a bit of digging. I don't want to say something that is just me speculating on something I'm not an expert at. So let me dig around a bit and get back to you. I think that was from Al.
Excellent. Thank you very much. Okay, so seeing the chat has died down, I think that will sort of mark the end of this particular discussion. And I want to thank you again for the excellent presentation and nice responses to some very interesting questions. I think it's a conversation that will continue for some time. And I don't know if Karen wanted to make more comments here or not, but I will turn it over to her to at least close the day. So thank you again, Jeremy.
Thanks, Brian. I did see one last question sneak in. So I'm going to sneak this one to you, Jeremy, because we do have 5 minutes. It's asking, lots of researchers and others working on geoengineering can present models inform what scale of engineering is needed to be effective or potential for geoengineering to cause new problems? Example. Oh, now it's scrolling through here. Example, avoid repeating the all fires are bad paradigm that started decades ago.
So yes, in short, models can totally explore geoengineering. Models are, like, I call them virtual laboratories. So in a model, it's very safe to put up a bunch of mirrors in space or do whatever and see what happens. And so models are one of the real tools that we are using now to try and understanding the positive and negative effects of different geoengineering options. In fact, it's one of the main tools because we can't experiment on that in the real world particularly easily, nor should we. So models do help us understand geoengineering impacts, both positive and negative.
Thanks, Jeremy. All right, well, thank you so much, Jeremy, for that. I know that we gave you a very large ask to cover fundamentals of climate in an hour. As Jeremy said during our earlier conversation, there are many points in his talk that you could get into at a PhD thesis kind of level. So I appreciate you trying to distill that down and provide the information. If anyone has any questions that come up after the presentation, you can send them in to us at wildfire@ualberta.ca. That question that Jeremy was going to look up, I'll ask you to please send me a response if you could, and perhaps when we upload this video to YouTube, we can include it in the caption description of the YouTube video for anyone that was interested. So with that, I want to say thank you everyone for coming. As you all know, this is part of a 4-part series, so please join us next week to look back at the historical. We're going to have Tricia Hook, who is a climate change impact technician, dendrochronology and forest health from Northern Forestry Center, and Kendrick Brown, research scientist focused on historical climate and fire reconstructions based on sediment coring from the Pacific Forestry Center. And our moderator is going to be Dr. Jill Harvey, who is the Canada Research Chair in Fire Ecology and Assistant Professor at Thompson Rivers University. So that'll be next Friday, same time, same place. Head over to our website, canadawildfire.org, to register and learn more, and we'll see you all next week. Thank you.